how Newton might interpret gravity was adequate to permit us to fly from the Earth to the Moon. At any point, get yourself lost in the ticking hands of time, contemplating whether how we might interpret it is simply the tip of the worldly iceberg. On its head, his disclosure isn't simply a hypothesis. It is a key that could open the ways to the secrets of the universe, uncovering a cosmos more multifaceted and moving than we ever thought possible. How does Brian Cox's new hypothesis challenge our customary comprehension of time, and what are the potential implications for our perception of reality? Join us on a captivating exploration through the chronicles of time itself as we delve into Brian Cox's recently uncovered, groundbreaking hypothesis on the nature of time in the vast universe around us. Secrets are waiting to be revealed, and some of these secrets involve confounding elements of time and gravity, which are fundamental portions of our reality. Imagine a world where time behaves strangely. It can either slow down or speed up. Additionally, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a different turn. Albert Einstein, a notable name, provided us with a new way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves in various circumstances, particularly when traveling at extremely high speeds. It all started in the early 20th century when Einstein proposed two remarkable theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of space and time. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous idea that time can expand or slow down under certain circumstances. One intriguing thought experiment to explain time dilation is the light clock. Imagine being inside a spaceship moving extraordinarily fast, almost at the speed of light. Inside the spaceship, there is a beam of light bouncing between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers. Therefore, the light beam must appear to travel along a longer diagonal path. The time it takes for the light to complete its journey should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the outside observer, it would seem that more time is required for the light to complete its venture. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. In this scenario, time behaves differently depending on motion. Understanding how things change when they move fast, known as relativistic effects, isn't just a theoretical idea. Scientists use large machines called particle accelerators, like the Large Hadron Collider, to make particles move extremely fast, nearly at the speed of light. When objects move this quickly, we need to think about time in a special way to make accurate predictions and measurements. Albert Einstein came up with the special theory of relativity in 1905, and it revolutionized how we see the universe, particularly regarding time and movement. This theory challenges our usual thinking. It says that the basic rules of physics are the same for everyone, even if they're not moving, which is different from our everyday experience, where we might think that if something is already moving and we add more speed, it gets faster. Yet, Einstein's theory says there's a maximum speed that nothing can exceed, which is the speed of light. In this view, events that seem to happen simultaneously for us might not appear that way for people moving around nearly as fast as light. Another concept from this unique perspective is length contraction. This means that if something is moving, it appears shorter in the direction it's moving when viewed from a stationary point. Then there's the famous equation. Equals 2 equals mc 2, which shows how energy and mass can transform into each other. This is crucial for understanding how tiny particles behave when they're moving super fast, and also for phenomena like what happens when atoms split in nuclear reactions. In the real world, special relativity isn't just an abstract theory, it's something we use in everyday technologies like GPS. When GPS satellites send messages to your device, they're moving, and because of this motion, time acts slightly differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't the same everywhere. it depends on how things are moving. This idea challenges our understanding of space and time, suggesting that our usual understanding of the universe is slightly off. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Some key ideas, like the speed of light always remaining constant and how energy and mass are interconnected, have been proven by numerous experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory dives deep into the connection between gravity and the structure of the universe. It shakes up the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because space and time are curved or warped. It's like saying, hey, gravity isn't a mysterious force. It's just how things naturally move in the universe. According to Brian Cox's understanding, general relativity means thinking of the universe as a four-dimensional entity, combining 3 dimensions of space and 1 of time. In this framework, large objects like stars, planets, and even us shape the fabric of space-time around them. This shaping is gravity. Imagine space-time like a big, stretchy blanket. When something heavy, like Earth, is placed on it, it creates a dent in the blanket. If you place something smaller, like a ball, near Earth, it will roll toward this dent. This is similar to how objects behave due to gravity, not as some mysterious force but as a response to the curvature of spacetime. General relativity offers a powerful explanation for how things move in our solar system, such as planets orbiting the Sun. It can accurately tell us the paths these planets take, including how Earth follows an oval-shaped orbit around the Sun. According to Brian, this differs from the old idea of gravity simply arranging things, which struggles to explain why planets move as they do. The novel idea is that space and time are curved like a flexible fabric, which aligns better with what we observe. A pivotal moment that demonstrated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's mass would cause the starlight to bend slightly during the eclipse. The observations matched Einstein's predictions, confirming the theory's validity. Just as motion can alter how we experience time according to special relativity, gravity also affects time. Where gravity is particularly strong, time moves more slowly compared to areas with weaker gravity. So, if you stood close to a massive object like a black hole, your clock would tick more slowly than one positioned far from this powerful mass. General relativity introduces black holes, which are regions where gravity is extremely intense. Inside a black hole, the gravitational force is so strong that nothing, not even light, can escape. The boundary surrounding a black hole is called the event horizon, and it's like a point of no return. Once something crosses this threshold, it's pulled into the black hole with no chance of escape. Einstein's theory of general relativity has significant implications for the structure of the universe. Initially, he added something called a cosmological constant to his equations because he believed the universe was static. However, when we discovered it is expanding, he referred to this as a major mistake. The idea of an expanding universe based on general relativity is a fundamental part of the Big Bang theory, which explains how the universe began. Another important concept from general relativity is gravitational waves. These are ripples in the fabric of spacetime caused by massive objects moving quickly, like when black holes or neutron stars merge. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory directly detected gravitational waves, providing evidence for another aspect of Einstein's theory. Over time, scientists have conducted various experiments to test if general relativity is accurate, and it has proven correct each time. Whether by observing planetary motion, the bending of starlight, or the detection of gravitational waves, general relativity remains a robust theory.